Video course on statistics. From basics to advanced subjects. Dr. Yahya El-Maghazi. Professor Emeritus at Auburn University, Alabama, USA. Former Dean of Science, Technology, Math, Engineering at Ocean County College, New Jersey. A visiting professor at a number of universities including Rowan University, Keene University, and Montclair University, New Jersey, USA.
Dr. Yahya El-Maghazi is the founder and the president of L-Learning LLC, a consulting education organization.
Probability Analysis. Part 5-2. Applications of the Standard Normal Distribution.
Now we're going to move to some practical examples to see how we can make use of the applications or the tools we have so far in real world examples. So let's go for the session and see how we can actually use the area under the normal curve in getting useful information in real applications. First, we need to emphasize a few steps that one has to do or has to follow in order to use the standard normal curve or the standard normal table. As I mentioned in the previous session, it's always useful to sketch the normal curve associated with the variable to describe the problem in question. Step 2 is to shade the region of interest and mark its delimiting x values, so we will know what region or what area we are after. Step 3 is to calculate the z-scores corresponding to the x values using the transformation of z equal x minus mu divided by sigma, which we discussed in the previous sessions. 4 is to use the standard normal distribution table to find the area under the standard normal curve delimited by the z-score. So now we're moving from the x to the z. Finally, is to express the findings back into x values, as we will see by example. So 5 basic steps: sketch the normal distribution, shade the region of interest, calculate the z-score, use the standard normal distribution table to find the area, and then express your findings in terms of x. Let's see how these steps apply to any example that we deal with. Here is an example. According to the controversial 2002 book titled The IQ and the Wealth of Nations, the average IQ test score of the world was 88, and the standard deviation was 12. Now, in case you don't know, here are the common criteria that are used to describe people IQ. Anything below 70 is extremely low IQ. 70 to 79 is borderline. 80 to 89 is low average. 90 to 109 is average. 110 to 119 is high average. 120 to 129 is superior. And 130 or plus is very superior. Regardless whether we agree with these criteria or not, let's deal with the problem. The findings said that 88 is the average score of the IQ worldwide, and 12 is the standard deviation. Now, the question here is to determine the percent of people in the world that their intelligences are considered above average or better. That's IQ greater than or equal the 110. That's above average or better. The second question is to determine the percent of people in the world that their intelligence are or is considered average, meaning 90 to 109. Well, all what we have here is two parameters, or values of two parameters, mu and sigma. So we have the average mu being 88 and the standard deviation sigma equal 12. And provided that we trust the values of these parameters, because that's the key issue, is to trust the values and make sure that these values are reliable, then we can use the features of the normal distribution and the transformation that we discussed before to answer any question associated with the data. So the first question: determine the percent of people in the world that their intelligence is considered above average or better. Let's see that. Here is a normal distribution, and here is the average, and the standard deviation, as we know now, is 12. So at 110 or more, we can, after we sketch the normal distribution, which is the first step, we can kind of identify where is the 110 is going to be, say somewhere in here. So now we very much know where is the 110 by rough sketching of the normal distribution. We also know what area that's desired. That's the percent of greater than or equal 110. So we're talking about this shaded area here. So that's the first step. We sketch, we identify the values of x as specified by the problem or the question being addressed. And now we know what area that we are after, what area that we need to determine. The next step is we are fully aware that in order to get the area under the curve, our normal table will only give us the area from minus infinity to the z value, or whatever the x value is required. So we need to keep that in mind. So now, with this in mind, here is the sketch of the normal distribution. Here is the value of x desired. Here is the area required. And we can now use the transformation z being x minus mu divided by sigma, where as x is 110, mu is 88, and sigma is 12. Using that, we have a value of z of 1.833. So now I can go to the standard normal curve. I can sketch that actually. And we know how it spans. It spans from about minus 3 all the way to 3. And the center is 0. And if z is 1.833, then it's somewhere in here. And now I'm after this area here. But the normal table will not give us this area. Instead, it will give us this area. So if I go here and look at the normal table, I can see that at 1.83, which is this one here, 1.8, 3 is direction, I will have an area of 0.9664. And what does that mean? It means this entire area from minus infinity to z is 0.9664. But that's not the area that I'm after. I'm after this shaded area here. But I also know that the entire area under the curve is 1. So 1 minus this area will give me this shaded area. Or in percentage, this is about 96.6%. So what we are talking about here is about 3.4% or 0.0336. Okay? So we have a 3.4% of people that have above average or better IQ according to the parameters we have. So in summary, we start out with a sketch in the normal distribution. We then identify the x values of interest. We then convert the x values into a z value, and then we obtained the area under the curve from the normal table, and these are the steps that we discussed earlier. Now, if you want to get the percent of people that have an IQ from 90 to 109, we will do the same steps. We have the normal curve, as you can see here. We will identify the x values. Here is the 90 and here is the 109, meaning that we need the area in the middle or the shaded area here. Then we need to convert these x values into z values. And here is the conversion using the equation we discussed before, the z-score, x minus mu divided by sigma. And now this becomes a normal problem that we solved before of finding the area or the shaded area under the curve. Here is another example. A sawmill pays workers by the quantity of garments they make. The average annual pay per worker is 18,000 and the standard deviation is 4,000. So that leads us directly to sketching the normal distribution with a mean value of 18,000 and the standard deviation of 4,000. Now the question is, if we draw a worker randomly, then find the probability that the worker selected randomly earns between 13,000 and 20,000. Now these are two X values that we have to identify on the standard, on the normal curve. So here they are, 13,000 and 20,000. And the question is about the probability of a worker selected randomly earning any value in this range, which is expressed by the area under the curve, because the area under the curve is in essence a probability. Keep in mind that the normal distribution is a probability distribution. So again, as we did before, we will take these two values, convert them into z values. At 13,000, x minus mu divided by sigma is 13,000 minus 18, which is the mean, divided by sigma, which is the 4,000. That will give us minus 1.25. And keep in mind, the sign is very important. You cannot ignore the negative sign here. Otherwise, that will alter the answer. At x equal 20,000, we have a positive value of z because it's 20 minus the mean value of 18,000 divided by the standard deviation, and that gives us the z value. And now that we have the two z values, we can sketch the standard normal distribution, and now we have a problem that we dealt with before many times. We have the minus 125 to the left side of the curve, and we have the plus 0.5 to the right side of the curve, and we need the shaded area here. And how we do that? We go to the normal table, and at 0.5 we can find the area to the left, the entire area from minus infinity to z equal 0.5, which is 0.6915. This is the entire area. And at minus 1.25 we can go to the minus value table, which is 1.25, and that will give us an area of 0.1056, which is the small area here. And if we can subtract the big yellow area from the green area, that will give us the area desired. As you can see here, A at 0.5 minus A at minus 1.25, that will give us 0.5859 or a percent to 58.6%. So if we draw a sample or a worker randomly, the chance that this worker will be earning from 13,000 to 20,000 will be 0.58 or 58.6%. Another way to express that is about 58.6% of the workers are likely to earn from the two values, the 13,000 to the 20,000 specified in the problem. Here is another example. Suppose a technical institute was interested in the SAT math section with the hope to get students from the top 25%. Now we need to pay attention to this problem because it is the reverse problem. Meaning we're going to be given the area and we are looking for the z value. So in the state this institute is located, the average score in the SAT math section was 550 and the standard deviation was 30. And the question is, what would be the score this institute would accept? Now keep in mind that this institute will take the top 25%. And once again, we sketch the normal distribution, as you can see here, with well-identified mean value. Standard deviation is identified. And once we start doing that, then we start looking at the top 25%. Now how are we going to do that? Here is a standard normal table. And here is a rough sketch of the 25% to the right, because that's the top 25%, meaning the area to the left is 75%. Now we have an area and we need the corresponding z value. We go to the table and we look for what area we're going to look at. We are not going to look for the right area because that's not the area given by the table. We're going to look at the left area, which is the 0.75. Now looking at this area, it's somewhere in here. It's not exactly 0.75, but it is 0.7486, as close as it can get to the 0.75. At this area, our z value is 0.67. As you can see here, 0.6 from the first column and 0.7 from the first row. So our z value is 0.670. Now that doesn't finish the problem, because we still need to take that z value and convert it back to an actual score. And the way we do that is by using the z formula. What we have here is z equal 0.607. Now z is equal x minus mu divided by sigma. Now x minus mu divided by 30 equal 0.67, and that by solving this simple equation we can get the x value of 570.1. What does that mean? It means this institute, taking the top 25%, will have to take any score at 570 or more in order to satisfy their acceptance criteria. What we covered here is actually few applications that gives us a good idea about how we can use the normal distribution to solve real examples and reveal important information. Using Microsoft Excel to find the area under the normal distribution curve. We see how easy it is to find the area under the curve. But in case you don't have a normal table accessible, then you can use Excel functions to do that. For example, determine the area to the left, that's the cumulative area of a certain value of x, say 109, in a normal distribution with a mean value of 88 and the standard deviation of 12. Well, we know about the Excel function. We can click on this function here, and that will give us this menu here, and we can click on statistical so that we can perform statistical functions. And the key here is to go to the normal distribution menu. That is this menu here, norm dist, that normal distribution. But as you do that, you have to keep in mind what you are trying to do. We have a distribution that has a mean value of 88 and a standard deviation of 12. And we are interested in a value of x of 109. So when you click OK here, what we're going to get is this menu here. Now here is the x value, 109. Here is the mean value of 88. And here is the standard deviation of 12. Now when we say true, true here means versus false, as we discussed before. It simply means the cumulative area from minus infinity to the z value corresponding to the 109. Now Excel is not going to give you the z value because it will do this transformation for you in the background. It will only give you the area. So it will save you from doing the calculations. I prefer myself to perform this type of analysis manually, but if you need to use the normal curve, the Excel spreadsheet, given the fact that you don't have the table, then this is the easiest way to do it. We now can move to a more important application of the Excel spreadsheet, and that is simulating a whole population using a normal distribution. That is simulating a variable associated with a population using the normal distribution. Previously, when we discussed the probability distributions for discrete variables, we showed you how to do that using the random number generated functions or tools in Excel. We will use the same tools now, so hopefully you are a little bit familiar with what we will discuss. So let's go to the slides and see how we do that. In fact, we're also going to do it in Excel to show you how simple and easy it is. All right, what we have here is we need to use Excel to generate a distribution. That's a probability distribution. So let's take an example. The total sales revenue per week of a company follows a normal distribution with a mean value of 100,000 and a standard deviation of 15,000. And the question is generate a normal distribution for this sales revenues per week using Excel data analysis. Let me go over the analysis in the slideshow first before we go to Excel. You keep in mind that your mu is 100,000 and your sigma is 15,000. So we're going to go to data, and from data we're going to go to data analysis. And in data analysis you're going to go to the random number generation as we did before. And in the random number generation, you will have this menu here. We have the number of variables. We're dealing with one, which is the sales revenue. Hopefully you have prepared a cell or a label called sales revenue. And then here is the number of random numbers we're going to generate, 1,000. And then you will select the normal distribution. Previously, we selected the binomial, which prompted us to the parameters of the binomial, the P and N, or we selected the Poisson, which prompted us to the parameter of the Poisson, which was lambda, if you remember. Now that we are selecting the normal distribution, it will prompt us to the parameters of the normal distribution. That is the mean value and the standard deviation. And once we do that, we click output or assign an output, and here we go. We can actually generate random numbers of the entire population or 1,000 of the population. As you can see here, here are different values of sales values generated using the random number generation. Of course, the column goes all the way down to 1,000, but it's only showing a small part here. And now we can perform descriptive statistics in the data using the descriptive statistics analysis tools. Here is the input range, which is the entire column. We can assign an output, we can do summary statistics, and we can click OK, and that will give us the descriptive statistics. Here is the mean value of the revenue, here is the median, the mode, the minimum, the maximum, and so on. Notice that the mean value is close to the $100,000, which we specified as our average of this population when we generated the normal distribution. And if we have that, we can create a bin range, and from the bin range we can create a histogram or a distribution of the sales revenue. Let me now go to Excel and do that step by step. Here is the Excel spreadsheet, and we're going to talk. Let me just remind myself of the values. We have a mean value of 100,000, and we have standard deviation of 15. I think it was 15,000. So this value here should actually be 15,000. Very good. So these are the two parameters that we need in order to generate the sales value data. So let's go here and put a label. We're going to call it sales revenue. Okay, and we now can go to data, data analysis, random number generation. We click OK, and as we did in the slides, we're going to use one variable, which is the sales revenue. That's the one that I prepared and title for here. And let us generate, say, 1,000 values of sales revenues. And since we selected a normal distribution, we will have to put the mean and the standard deviation given. Our mean value is 100,000, and our standard deviation is 15,000. So we have a mean value of 100,000 and the standard deviation of 15,000. And that's all what we have to do. Then we can specify an output. We can click on here and anchor it by clicking again here and go under here. So the values that we will generate will all be under this title here. That's all what we have to do. Now I want to point out something. You have here a random seed window. And what does that means? If you ever want to use the same data that you generated once, you can have an ID or a seed number here that will allow you to reproduce the same data again. That's if you have to. We will not do that in here. We simply used one variable, 1000 random numbers generated, a normal distribution. We inserted the parameters of the distribution mu and sigma, and we specified an output, and we say okay, and we have now 1000 values of the sales revenue data that we just generated. As you can see here, we can go down the column all the way to 1000 values. In fact, it goes all the way to cell 1006, given the 1000 observations. So in a fraction of a second, we were able to generate 1000 values of sales revenue. And if we don't like the too many decimals, you can click on the right button of the mouse to format cells, and you can go to number, and you can control the number of decimal places here. Since these are in the hundreds of thousands of orders, we may want to get rid of any decimals, and now we have values that are without decimals. These are the 1000 values of sales revenue. Now, are these values accurate? Of course they are. However, they are as accurate as the parameters that we are given. If these parameters are inaccurate, then these values will definitely be not accurate. So you want to make sure before you generate random numbers that the parameters that you are using, in this case the mean and the standard deviation, are accurate. So now, all of a sudden, we have 1000 observations that did not exist a minute ago via the random number generation. And what does that mean? It means we can do any type of analysis with it. We can do descriptive statistics, for example. I can go to descriptive statistics in the data analysis tools, click OK, and now I have the cell going from H5 all the way to H1006. This is, or I can actually block all of these with the mouse to obtain the input range. I have labels in the first cell. I can put the output somewhere in here, and I can use summary statistics, and I can say okay. And now let me just go over this again. I can block all the input values, as you can see here, the 1000 values, and that will be my input range, and I can have my output somewhere, summary statistics, and we say okay. And now we have our descriptive statistics of the generated data of sales revenue. And as you can see here, again, if we want to get rid of the decimals, we can use 1 decimals or less. And we now have a mean value that we can see. We have a range that we can see. We have a minimum and a maximum. And we have the median and the standard deviation. Notice something here, that if you observe the mean value and the median and the mode, you will see that these 3 values are more or less the same. Keep in mind, we're generating random numbers here. So they are not going to be exactly identical, but they are very close. And that's a good indication that what we are actually generating is a normal distribution, because in a normal distribution, the mean, the median, and the mode will be the same. Okay? Also notice that our standard deviation is about 15,000. It's 15,268. And keep in mind that that was one of the 2 parameters that we have to insert in the Excel data analysis. So the mean was satisfied as almost 100,000, and the standard deviation was satisfied, and we should not be surprised because that is how we generated the data. Now we have the descriptive statistics. I can go to bin range, and I can develop a histogram. Now notice we're starting here a minimum value of 54,427, a maximum value of 144. So I can start a little bit lower than the minimum at 50,000, and I can move on If this is a sales revenue, then perhaps I want to go at 5,000 or 10,000 interval. So if I say plus and I go up and add 5,000, that will give me an interval of 5. And now I can copy this and go down, paste the calculations all the way. I have here 105. I still need to go further down, all the way to 155. I really need only to 145. So I can delete this and delete this. And what I just created is a bin range in order to construct a histogram. That bin range begins at 50,000. It goes all the way to 145,000. Notice that the minimum value was 54, so I started a little bit lower than the minimum. And the maximum value was 143, so I ended up a little bit higher than the maximum. And now I have included all my data. I can now go to data analysis, histogram. Okay, our input range will be all the data that we generated, which is the sales revenue data. So we're going to do the same thing that we did with this descriptive statistics, inputting all the data that we generated. Our bin range will be the bin range we pre-constructed. As you can see here, I'm going to go to the bin range, and I'm going to give this column to Excel. So now Excel have the input range and they have the bin range. There are labels in both the bin range first row and the data first row. Then my output, I normally put it next to the bin range just to make sure that we did it correctly. So I'm going to put it here, and we're going to do cumulative curve and output, chart output, and we say okay. And what does that mean? It means we now have the normal distribution that we have created. And as you can see here, that didn't take much time. And of course, we can separate the cumulative from the normal distribution from the actual histogram by copying this, pasting it here. So now I have two copies. I can go in the top copy and delete the cumulative curve, and I can go in the bottom copy and delete the histogram. And now I have a cumulative curve in one case and the histogram in the other. If you don't like those gaps, then we can easily come here and click on the right button by clicking on the series and just say close the gap or no gaps. And now we have a nice distribution that is continuous and it has no gaps. We can also change the color if we want. I mean, we can click on the series, then click on the right button, go to Format Data Series. We can do the fill, solid fill yellow. We can also make the border color black. And now we have a nice distribution. Now keep in mind that this is a histogram. We want this histogram to be a probability curve. So let me go over this for just a few seconds. I need to convert this histogram into a probability distribution. Now, if you go back to the frequency table developed or constructed by Excel, what we have here is the bin, and what we have here is the frequency. Now, what I need to do to convert this into a probability distribution is to convert the frequency into relative frequency. And how we do that? Well, we're going to come here and we're going to add a column called relative frequency. Really, it is the probability. Because as we mentioned in the sessions, probability is basically the relative frequency. And now we need each frequency to be divided by the total frequency in order to get a relative frequency. Notice, if I get the sum of all of these, this is equal sum, and I go up here, this sum is better be the 1,000 observation that we constructed. Remember, we generated 1,000 observation. So the sum of all the frequencies is 1,000. So now if I want to convert any frequency into a relative frequency, such as this one here or this one, I'm going to come here and press equal and go all the way to frequency and do a slash, which is a division, and divide that frequency by 1,000. Here again, I can go to the next cell, equal, move to frequency, slash, and divide this by 1000. I don't actually have to do that for each observation because I can copy the calculation and go down and paste it, and that will repeat the calculations for all the cells or all the frequencies, as you can see here. So what I just did, simply I created a relative frequency column or a probability column. Notice also that if I get the sum of this column here by coming here and say equal sum, open a parentheses, and go up and add up all of these values of probability, this sum is better be 1. And as you can see, the sum of probability is 1, just like the sum of all the observations was 1000. Now that I have a probability column, I can easily copy this. I can block this column, as you can see here with the mouse, and copy, and I can go in my graph and click on the graph and right button and paste. Now you will not see anything, as you can see here, because the two distributions superimposed or coincided. So how we do that, how we create a probability distribution, now that I have, if you notice, two series here, one for the frequency and one for the relative frequency or the probability, I can easily delete the histogram or the frequency. If I click on the histogram, click on the right button and delete, what I see now is a true probability distribution. In fact, if you look at the values here, you will see that these values in the vertical axis are actually not frequencies, but rather probability. I can come here and change this column into px or probability. I can remove this or change it from histogram to probability distribution of sales revenue. And I can even delete the series because I know now what is this. This is sales revenue. I can change the bin range and title it sales revenue because that's the actual meaning of these values here. And I can also alter the series color. I can make this yellow just to make it more customized. I can make the border different colors. This is the border color. I'm going to make it black. The fill, I'm going to make it yellow. And now we have a nice looking probability distribution. If you don't like the more, by the way, you can always come here in the frequency table and simply erase more. If you delete more, you will not see more in the probability distribution or the histogram. And what's good about that now is in a few seconds we were able to construct a normal distribution that follow the parameters we did. I can then add comments here, or I can observe and examine and describe the distribution that I have, or obtain many informations as we discussed before. The point I want to make here is what we just did is essentially a histogram, but it is in the form of a probability distribution. It has classes of values, it has constant interval, it has a vertical axis that we called it probability or relative frequency. And if you go back to the sessions where we were able to obtain lots of information from the histogram and from the cumulative frequency curve, you can apply the same concepts that you learned in the previous session of histograms and the cumulative frequency distribution on the probability distribution concepts. So the idea here is how to simulate a population. We started out with two values, the average of the population of sales revenues and the standard deviation. And if we can do that, then we can generate a whole population, 1,000 observations. That's 1,000 random values of sales revenues. And to me, that's really amazing that you can simulate a whole population this way. And these values are accurate. They are as accurate as the parameters that you are inserting. If your mu and sigma are accurate, then the generated random numbers will be accurate. And you can use these numbers into descriptive statistics, histograms, probability curve, probability distributions, and obtain any information that you need.
Video course on statistics. From basics to advanced subjects. Dr. Yahya El-Maghazi, Professor Emeritus at Auburn University, Alabama, USA. Former Dean of Science, Technology, Math, Engineering at Ocean County College, New Jersey. A visiting professor at a number of universities including Rowan University, Keene University, and Montclair University, New Jersey, USA.
Dr. Yahya El-Maghazi is the founder and the president of L Learning LLC, a consulting education organization.